100,000 years ago, up to 1 million humans roamed the Earth. And yet, about 70,000 years ago, a population of just a few thousand people may have given rise to all modern humans. Something happened. Something big. Something that changed the course of human development. How did this happen? And does our 21st century civilization face the same terrifying threat? There are more than 6 billion people alive in the world today. Humans have adapted to the different conditions across the planet by developing a wide variety of different physical characteristics. We come in a huge range of colors, shapes, and sizes. But the really interesting thing is not how different we appear on the surface, but how similar we all are underneath. Professor Todd Disotell of New York University studies DNA, a kind of human barcode for our inherited physical characteristics. It turns out there is a difference of only about 0.1% in the genetic information held in the DNA molecule between any two people, however different they may look, and wherever in the world they originally come from. We all have more in common with each other than we might have thought.
I find it absolutely fascinating how little genetic diversity there are amongst people throughout the world. You see people with different skin color, head shapes, hair types, and all of those things. Those differences seem to really be skin deep when we get down to the genetics.
In fact, there is less variation in the DNA of all of the people alive on the planet today than exists in just one troop of chimpanzees in West Africa. The small genetic diversity in our huge population may tell us something important about our prehistoric past. That something happened to erase most of the human DNA record. Something that could have decimated the numbers of our ancestors. It's called a genetic bottleneck, a population collapse that wipes out much of the DNA record. Nowadays, they're commonly seen in endangered species. It's like what happens if you shake a range of colored balls out of a glass container.
Here I have a large variable population represented by the 5 different colored gumballs. If this population shrinks by going through what we call a genetic bottleneck, here actually represented by a real bottle, I end up with a smaller pool with less genetic diversity.
The human DNA record suggests that something may have driven our ancestors to the brink of extinction. The evidence in our genes may also tell us when this happened, and how many prehistoric survivors made it through the genetic bottleneck. Scientists can estimate the size of human population from the past using mitochondria, a sort of cellular battery pack that has its own DNA. Mitochondrial DNA is only inherited from the mother and does not combine with genetic information from the father. So, starting with the total range of these genes identified in our modern population, scientists can track back along the exclusively female line and estimate the number of childbearing women in the population of earlier generations. And the DNA that is passed to a child is not always a perfect copy of the parental DNA. It's a bit like photocopying a photograph and then photocopying the copy over and over again. Each imperfection carries forward to all the subsequent copies, and over time, the picture can change significantly.
So this is how I mutate after 20 generations of photocopying.
Scientists can estimate the date and human population after a genetic bottleneck by comparing the rate of mutation and the present range of mitochondrial DNA variation.
By looking at the pattern of mitochondrial mutations that we see on the planet today and using the known mutation rate of mitochondria, I can estimate that between 50 and 100,000 years ago, there was only a few thousand individuals that gave rise to the populations that we see on the planet today.
In other words, every single one of our 6 billion plus population may be directly descended from a tiny group of people. Maybe even as few as 5,000 in total, who lived between 50,000 and 100,000 years ago. That's equivalent to just one person for the entire modern population of Manhattan. If Dissertel is correct, then we all owe our existence to these few thousand survivors. Yet there may have been as many as 1 million prehistoric people alive before the start of the genetic bottleneck. Stone tools from more than 100,000 years ago have been found as far apart as Northern Europe and China. But how far had our species developed by this time? Were any of these creatures really human? The Natural History Museum in London is home to one of the largest ancient fossil collections in the world. Dr. Chris Stringer examined specimens from the collection to investigate how far our ancestors had evolved by the time of the earliest predicted start of this population bottleneck. Geneticists estimate that human evolution started about 6 million years ago, when the DNA of chimps and our species first separated. But the earliest signs of distinctly human characteristics emerged several million years later.
By about 2 million years ago, we appear to have the first creatures we can call human. The face is starting to show human features. We've got the beginning of the development of a prominent nose. The base of the skull shows us that these creatures were walking upright, and we've got the appearance of stone tools.
Paleontologists use brain size, traditionally measured from the volume of beads that fit in a skull, as a marker of human development. This 2 million year old human had a 600 cc brain, much larger than a chimpanzee, but less than half the volume of a modern human. Over the thousands of years that followed, human brain sizes increased. By 100,000 years ago, fossils such as this skull from Israel had modern human dimensions.
Essentially, this is a modern human skull. And it shows us that modern humans had evolved by this time. They may well have appeared, first of all, in Africa, as far back as 200,000 years ago.
By then, early humans were producing a more sophisticated range of tools to meet different needs.
In this case, this tool was probably used for its scraping surfaces, but we find they're shaping spear points, they're shaping tools probably for working wood, and so we're beginning to get the evolution of specialised technology.
And there are even clues that they were starting to think like us.
Well, we've recently discovered evidence of symbolism from 100,000 years ago. We've got shell beads, so people are using body adornment. They're sending messages to each other, if you like, the beginning of art and creativity, the sort of thing that we find with modern humans.
By 100,000 years ago, before the likely start of this genetic bottleneck, there were a range of prehistoric people living across much of the planet, including essentially modern humans. But some scientists believe that this intelligent, adaptable species was about to suffer a cataclysmic drop in numbers. So what apocalyptic event could have driven Stone Age man to the brink of extinction? A massive volcano? A terrifying tsunami? Or maybe a devastating asteroid impact? Some scientists believe that Stone Age humans suffered a genetic bottleneck between 50 and 100,000 years ago. From a global population of hundreds of thousands, the human race may have been sustained by a small group of only a few thousand people. Until recently, evidence of a catastrophic natural disaster that could have decimated the numbers of our Stone Age ancestors lay hidden in the frozen ice fields of Greenland. Tiny air bubbles are preserved in the Arctic ice. They hold detailed scientific information about the climate from when the water froze. Global temperatures can be estimated from the thickness of the ice layers. Aerosol and dust particles record information about natural events from that time. Scientists can date all this information. A new sheet of ice is deposited each year, so the annual records pile up, one on top of another, like pancakes in a diner. The individual layers are identified from ice cores, long cylinders of ice from below the frozen surface in Greenland that carry many thousands of years of environmental data. Professor Greg Zielinski of the University of Maine is a leading expert on the study of the ice core record. In 1993, he made a stunning discovery in this environmental time machine.
As I was investigating the record of the sulfuric acid in the ice core, I noticed about 75,000 years ago that was this very large spike or really very high concentration of sulfate. To have something that big was just so exciting that I wanted to investigate it more.
Zielinski had discovered the highest annual acid reading in the entire 110,000-year record of the Greenland ice core, which points towards a cataclysmic natural disaster.
This large amount of sulfuric acid really only has one potential source, and that would be an extremely large, massive volcanic eruption.
The unprecedented acid discovery in the ice core came from a huge volcano. Major eruptions blast out enormous quantities of gases, including sulfates, which turn into sulfuric acid in the atmosphere. The largest acid cloud of the 20th century resulted from the 1991 eruption at Mount Pinatubo in the Philippines, which ejected 20 million tons of sulfur dioxide. The acid in the ice core suggests that about 75,000 years earlier, there was an eruption 100 times bigger than Pinatubo, itself the largest for nearly a century. Most active volcanoes lie at the boundaries between the vast tectonic plates that make up the surface of the Earth. The most powerful super-eruption of the last 2 million years happened in Southeast Asia, on the Indonesian island of Sumatra. Lake Toba is an enormous body of water, 60 miles long by 20 miles wide. In 1929, Dutch geologist Van Bemmelen identified this location as a vast caldera, the hole left behind after an eruption has blasted enormous quantities of volcanic material into the atmosphere. In fact, much of this huge crater was formed following an immense super-eruption 75,000 years ago. In line with the timing of the record acid find in the ice core, this eruption, 3 times bigger than the last major event at the Yellowstone supervolcano, could be the devastating natural disaster which threatened the very future of our species. The shocking power of this volcano results from the chemistry of the rocks deep beneath the surface of the lake. Sumatra lies close to the boundary where the Indo-Australian tectonic plate pushes beneath the Eurasian plate at a rate of about 2 inches per year. The lower plate releases water, causing rock in the plate above it to melt and then rise as low-density magma. At surface level, this melted volcanic rock becomes lava. But it is the potential of magma trapped below ground to hold in gases that creates the explosive power of a volcano. Dr. David Walk of Rensselaer Polytechnic Institute in New York State studies the composition of the magma which caused the Toba eruption 75,000 years ago to understand why this event was so powerful. He describes the build-up of the liquid rock in the magma chamber as being like filling a bottle with a fizzy drink.
Like magmas, the soda has dissolved bubbles inside of it, dissolved gases. You can see the gases trying to work their way out there.
With bottles of cola, carbon dioxide can move easily through the drink and escape. This is like low-viscosity magma, found at volcanoes such as Kilauea in Hawaii, where gases bubble up through the liquid rock and lava ebbs out slowly at the surface. Walk tests magma from the 75,000-year-old eruption along with a control sample from a nearby Sumatran volcano to demonstrate why the Toba event must have been so violent. At 1300 degrees centigrade, or more than 2000 degrees Fahrenheit, the control sample melts. Even to the naked eye, the sample from the Toba magma is much more viscous, and so able to hold in more explosive volcanic gases than the control. A powerful microscope highlights holes in the melted Toba material. These are the spaces left behind after the huge volume of gases escaped during the super eruption.
It's the bubbles that are trapped, and they're trapped because of the high viscosity that makes the eruption so explosive.
75,000 years ago. Thousands of cubic miles of magma have accumulated beneath the Sumatran landscape, creating irresistible pressures on the surface. "200 cubic miles of ash blast out from Toba, covering an area more than 10 times the size of California. Over 2 billion tons of sulfuric acid explode into the atmosphere. This is the biggest eruption modern man has ever experienced. But how could one volcano drive the human race across the whole of the planet to the brink of extinction? Close to the volcano, the effects would have been apocalyptic. Imagine pyroclastic flows, superheated avalanches of volcanic material. They wipe out an area of more than 7,000 square miles of Sumatra. They vaporize anybody in their path. They extinguish all signs of life across the width of this vast island. An eruptive column up to 50 miles high ejected more than 200 cubic miles of ash into the atmosphere. We have experienced the lethal consequences of volcanic ash in recent times. When Mount Pinatubo in the Philippines erupted in 1991, the column reached a height of about 22 miles. Dennis Shows was a serviceman stationed at the nearby US Air Base.
You could see the volcano erupt because it looked like a cloud of ash rolling over the sky. Looks like something out of a movie.
Unfortunately, this was a horror show without a happy ending.
Everything was just gritty everywhere. All the branches were gone. All the vegetation was just covered and coated and everything just gone.
The Pinatubo eruption killed 320 people. Volcanic ash caused most of the deaths. But here, volcanologists identified the threat early. A mass evacuation saved up to 20,000 lives. At Toba, there would have been no warning system, and the super eruption 75,000 years ago ejected 200 times more volcanic debris than Pinatubo. The ash cloud would have covered an area in excess of 1 million square miles. Now, a new archaeological find gives a unique insight into the impact of this terrible downpour on Stone Age societies. In the year 2000, a layer of Toba ash some 4 yards deep was identified in southern India by Dr. Michael Petraglia of the Leverhulme Centre at the University of Cambridge.
It is a spectacular deposit, very thick sequence with archaeology associated with it. It's a one-of-a-kind find.
You're pretty far down.
In the immediate aftermath of the eruption, approximately 6 inches of ash fell on southern India. The first threat to the Stone Age hunter-gatherers would have come from breathing in this fine powder.
These particles are like little glass shards. And these glass shards, if they get into your lungs, they can cause all sorts of damage.
Once this deadly volcanic debris had settled, it polluted the environment the prehistoric hunter-gatherers lived off.
If this dust gets into water and you have to drink it, it can actually turn the water into poison. There are ancient plant fragments that I'm pulling out, and some of these plants might have died because of the super eruption itself.
The fall of an estimated 6 inches of Toba ash on India would have wiped out most plant life because the ash layer would have blocked out oxygen from the air, making the soil sterile. Ash from the much smaller Pinatubo eruption in 1991 devastated hundreds of square miles of agricultural land. Soil samples from Petraglia's site in southern India indicate that this area had supported extensive plant life.
Below the ash we find this clay, and we believe that marshy types of plants were in this environment.
This fertile soil was covered in a thick layer of barren ash, immediately creating a very hostile environment for vegetation.
The chemistry of this ash is such that the plants cannot survive in it.
This deadly ash would have covered much of India over the course of just a few days.
The landscape would have been blanketed by this ash, and therefore plants and animals would have had a very difficult time surviving.
But the problems created by the ash would have continued for years. In this part of the world, there is an annual monsoon season. In modern India, this causes major floods. 75,000 years ago, this huge yearly rainfall would have continually moved the millions of tons of volcanic matter from the Toba super-eruption, causing new perils for any Stone Age survivors.
During monsoonal seasons, what would have happened was the ash on the landscape would have been eroded off into streams and into rivers, therefore choking those systems.
The 4 yards thick layer of ash at Petraglia's dig probably built up as monsoon water carried the volcanic debris into waterways, blocking up the natural irrigation systems.
See, so you're finally digging.
Any survivors would have faced a bleak future in this barren, inhospitable environment. Archaeologists have discovered no human remains beneath the Toba ash layer. A collection of Stone Age tools is the only surviving testament to the society that existed here before the super eruption.
Well, what's so interesting is that we find these in great abundance below the ash. But once the ash came, it seems that those populations using these stone tools were no longer there.
Volcanic debris from the Toba eruption threatened hunter-gatherer societies over more than 1 million square miles. But long after the ash cloud scattered, Stone Age survivors across the globe faced a second peril. An acid cloud created by the 2 billion tons of sulfates blasted out by the supervolcano. Acid droplets in the stratosphere would have blocked out much of the sunlight, triggering a global 6-year volcanic winter. Professor Howard Griffiths of Cambridge University investigates the impact of this sudden climate change on plant life.
What our experiments have done have mimicked the effects that we'd expect to see following that volcanic eruption. We have reduced the light intensity, we've reduced the temperature, and we've reduced the water availability for plant growth.
Acid from the Toba eruption cut out up to 90% of available sunlight. But plants use energy from the sun to grow in a process called photosynthesis. Griffiths investigates the impact on his test specimens of dropping to the lowest light levels of the volcanic winter.
What we've got here is that the leaf has now stopped photosynthesizing altogether, so growth would stop.
The low sunlight levels resulting from the Toba eruption could completely halt plant growth. But the acid cloud also reduced global temperatures by as much as 30 degrees Fahrenheit. Griffiths applied this additional trauma to the experimental plants over a period of 2 weeks.
Here you can see there's some immediate effects with rather yellow gaps indicating a loss of photosynthetic activity. The low temperatures has really reduced the potential of this plant for growth.
To make matters worse, the volcanic winter would also have triggered a 10-fold drop in rainfall in some areas. A microscopic examination of test specimens that have suffered all of these environmental changes suggests that the combination of reduced sunlight, temperatures, and rainfall would have had a devastating effect on vegetation following the Toba eruption.
What our experiments have shown is that the combined stresses that were predicted to have accompanied the Toba eruption will have the effect of basically deforesting and defoliating the entire environment.
The super eruption 75,000 years ago caused a terrible volcanic winter that laid vegetation across the planet to waste. This could have decimated most modern human populations. But there were survivors, and it is their descendants who went on to make the world we know today. So who were these people? Geneticists can trace the movement of early humans by comparing DNA variations in different parts of the world. The region with the greatest genetic diversity is the most likely source of populations with more limited DNA variation. Professor Todd Dissertel of New York University compares this to a deck of cards.
If I take a full deck of cards and I shuffle it and then I deal them out, there'll be hearts, there'll be clubs, there'll be spades, there'll be diamonds. Then if I only take a small group of cards, let's say they're all red, no matter how often I shuffle them, all of the hands that I deal will always be red. So the greatest diversity we'll ever find is always from the founding population, in this case, the full deck of cards.
This pinpoints the most likely source of modern humanity to the region with the greatest genetic diversity, East Africa. In fact, there is likely to be more difference between the DNA of two neighbors in one village in East Africa than between a person of Southeast Asian descent and a person of Northern European descent.
The diversity that we see basically around the planet seems to be traced back to East Africa.
Many experts believe that our entire 6 billion population came from a band of only a few thousand people from East Africa about 60,000 years ago. But there is archaeological evidence of up to 1 million humans living across much of the globe tens of thousands of years earlier. Something seems to have happened to halt human development across most of the inhabited world in a kind of prehistoric game of risk. The Toba supereruption 75,000 years ago caused a devastating global volcanic winter. A small band of East African survivors of this apocalyptic natural disaster may have sustained the entire human race. Professor Stanley Ambrose of Illinois University believes that the supereruption did trigger a genetic bottleneck. And he has a theory on how a small group of East African hunter-gatherers adapted their behavior to withstand the harsh aftermath of the Toba volcano.
I think Toba changed the course of human history by forcing people to become cooperators as opposed to selfish defenders of their small territories.
Ambrose believes that just a few thousand of our prehistoric ancestors survived the genetic bottleneck by learning to work together, building up support networks, and developing more sophisticated forms of communication. He bases his theory on the movement between Stone Age communities of the materials used to produce prehistoric tools in Kenya, and in particular on a type of volcanic glass formed from lava called obsidian.
Things that made obsidian so valuable was that it was so sharp, like broken glass, which is what it is, that you could actually shave yourself with it.
Razor-sharp tools were a precious commodity in Stone Age times. People would have gone to great lengths to acquire obsidian. It is possible to work out which volcano the obsidian originally came from, so archaeologists can use it to track movement across the prehistoric landscape. Ambrose discovered that the tool-making materials at sites from before the Toba eruption were nearly all sourced locally. The stone came from inside the territorial boundaries of the hunter-gatherer community that lived there, suggesting that there was little communication between groups. A volcanic winter triggered by the supereruption, when temperatures in Africa dropped by up to 30 degrees Fahrenheit, rainfall fell by up to 90%, and much of the vegetation died, seems to have changed this. At archaeological digs from after Toba, such as this one near Ntuka, 60 miles west of Nairobi, most of the tools are made from obsidian, which Stone Age settlers had carried much greater distances from territories inhabited by other groups.
Well, there's a piece of obsidian. It's likely to have come from about 70 miles away. When I find obsidian out here, it doesn't just mean to me a stone tool, it symbolizes relationships, the ability to get across a territory.
The movement of the obsidian suggests that people traveled further in search of scarce resources in the bleak aftermath of the supereruption. But as Ambrose demonstrates when he retraces the route of our Stone Age ancestors to the obsidian source at Crater Lake Quarry, this is a tough territory to cross.
Driving around the African landscape is difficult enough. Doing it on foot with wild animals must have been a really incredible challenge for these people.
An experiment at Kenya's Hell's Gate National Park shows how grueling the 70-mile journey to the obsidian source would have been on foot. Daniel Shah is a fit, healthy guide from a nearby Maasai village.
The blood pressure is 100/60.
He starts at dawn from a local landmark, Fisher's Tower, and sets out to walk as many miles as he can through this tough terrain before returning here at sunset. Shah covers a fraction of the 70 miles separating the Stone Age settlement and Crater Lake Quarry over the course of an exhausting 12-hour trek.
He's walked 14.88 miles.
Prehistoric humans could have taken several days to get to the obsidian source, crossing the territories of other hunter-gatherer groups on the way.
They would have to either avoid encounters with the people who lived in this area or have very good relationships with them. They probably preferred to have good relationships because I don't think any rock is worth your life.
Ambrose believes that the tough East African terrain would have forced people to cooperate with their neighbours as they sought high-grade tool-making materials from obsidian sources such as Crater Lake Quarry.
I think this is a great place to come and collect obsidian if you're a Stone Age person because you can pick and choose the pieces you like very easily. So it's sort of like a supermarket where you can just come and pick what you'd like off the shelves.
This site lies on the edge of an ancient volcano. The obsidian was originally magma that rose when the volcano was active and became lava at the surface.
This glass probably cooled very quickly, and when it cools quickly, it prevents crystals from forming.
The quality of the obsidian will also depend on the chemical composition of the lava and on how the rock is preserved in the earth. The obsidian at this site can be easily worked to produce the razor-sharp edges our prehistoric ancestors used for hunting and preparing meat.
This kind of volcanic glass is very good for making stone tools because it has such a fine grain or no grain at all, and that makes the edge extraordinarily sharp.
And there is still evidence at the site of the quarrying work of the Stone Age hunter-gatherers.
Well, what we see here is a very large block of obsidian that looked quite desirable, and you can see here where they tried digging it out, and I think they gave up. It may have been just too much work, may have been in a too precarious a position, or it may have just been too big to carry. But it's a nice piece.
The sophisticated tools that can be made from high-quality obsidian would have helped the ancient Africans to survive in the barren post-Toba landscape. But Ambrose believes that the communication skills people learnt as they collected tool-making materials would prove to be more significant over the centuries that followed.
The fact that people came from such long distances implies a new set of skills for negotiating, traveling across people's territories. I think that was the last step in the development of language.
He believes that new skills our ancestors developed in the tough climate after the Toba eruption changed the course of human development across the planet.
Toba probably ultimately allowed people to get out of Africa and populate the rest of the world. This was just the beginning of a revolution that I think has continued.
If the Toba theory is correct, then all of the 6 billion people alive today are descendants of a group of just a few thousand people from equatorial Africa who learnt a whole new set of skills to survive the horrifying aftermath of this super eruption. So are there any lessons for us here in the 21st century? If the Toba supervolcano made our modern civilization, could it also destroy it? 75,000 years ago, the most powerful supervolcano modern man has ever experienced erupted in Indonesia. It may even have driven the human race to the brink of extinction. Lake Toba, on the island of Sumatra, formed in the crater left behind after 200 cubic miles of ash had blasted into the atmosphere. Nowadays, this is a peaceful place, inhabited by fishing communities and visited by tourists intrigued by this vast lake and the hot springs that are a rare reminder of its volcanic past. But this calm could be shattered at any moment in this region of high seismic activity.
15, 20 feet tall. Easy.
December 2004. An earthquake in the Indian Ocean launches the most deadly tsunami in history, raising fears of new volcanic activity in Indonesia. The vast readjustment in the Earth's crust which triggered this tragic series of events happened on the Sumatran Fault, part of the same geological system that caused the super eruption on the island 75,000 years earlier. Many scientists believe there is a direct link between earthquake activity and volcanic activity, but for Toba to erupt, it would need to have a large volume of magma already built up beneath the surface. Professor Rob McCaffrey of Rensselaer Polytechnic Institute in New York State made a study of volcanic activity beneath Lake Toba in 2001. A simple demonstration in the college grounds shows how he was able to use sound waves to understand the subterranean geology in Sumatra. Students position a series of sensors at equal distances from a source of sound waves, in this case, a hammer.
There you go.
The sound waves from the hammer blow move through different materials at different speeds. So even though the sensors are the same distance away, it reaches some of them more quickly.
Here's a good one. Waves that travel through the walkways arrived sooner than the waves that travel through the soil underneath the grass. That's because the walkways are much more consolidated.
So by analyzing sound waves at different points, scientists can build up a picture of the geological features they have passed through. McCaffrey sets up sensors around Lake Toba to measure the sound waves generated by low-level earthquakes. His readings reveal an immense volcanic system hidden deep beneath the lake.
Our tomography results suggest that there are two separate chambers, a large one in the south and a smaller one in the north.
And there's an alarm. There are signs of new activity at Toba.
If we're interpreting these things correctly, it looks like there is magma feeding directly into the chamber and rejuvenating the volcano today.
There is still volcanic activity at the site of the largest eruption of the last 2 million years. To determine if a major new eruption is imminent, experts look for telltale signs of movement in the ground above the magma chamber. In 1993, McCaffrey took GPS positioning measurements all around Toba. In 2001, he returned to the site to look for surface changes.
To our surprise, things just weren't moving at all. We could measure to within a 1/16 of an inch, and at that level, we didn't see any movement at all. Well, I would say that I don't expect anything catastrophic to happen at Toba, within my lifetime anyway.
Toba may be safe for the immediate future, but what about the dozens of other ancient supervolcano sites, including perhaps the most famous at Yellowstone National Park? At Yellowstone, there is clear evidence of a volcanic past in the rugged landscape. And a series of geysers, fumaroles and hot springs reveal continuing subterranean activity. Enough to have raised fears of a new super-eruption brewing beneath the surface here. The problem is that we have no record of exactly what the warning signs are for these cataclysmic events. And this is one of the greatest concerns for Professor Bill Maguire, Director of the Benfield Hazard Research Centre at University College London.
The trouble with super eruptions is that we've never experienced one in modern times, so we don't know exactly what we will see before one of these eruptions. We may get months of warning, we may only get weeks, we may only get days.
We don't even know where the next super eruption is likely to happen.
they may occur where there hasn't been any eruption before. So magma may have been accumulating over the last few hundred years, and the first we'll know about it is when that magma breaks the surface and we get one of these huge eruptions.
And super eruptions like Toba are on a completely different scale from the volcanoes we have experienced in modern times, such as Montserrat in the Caribbean, Etna in Sicily, or Mount Pinatubo in the Philippines.
If this ball represents the volume of material ejected by Pinatubo, which was one of the biggest eruptions of the 20th century, then this basketball represents the amount of material ejected by the Toba eruption. Now, Pinatubo actually cooled things down by maybe ½ a degree. It actually slowed down global warming. So you can imagine what an eruption of this size would do to the global climate.
Our modern infrastructure is not designed to cope with Toba-level climate change, like temperature drops of up to 30 degrees Fahrenheit or 90% rainfall reductions. A modern supervolcano could be 1,000 times more devastating than the worst natural disasters on record.
I think the next super eruption will kill perhaps 1 billion people through starvation. It will bring the global economy to the edge of complete collapse, and it will be the greatest disaster that our civilizations ever had to cope with.
The awesome dimensions of the Toba caldera are a somber reminder of the power of nature. The super eruption here 75,000 years ago may have threatened the very future of the human race. The chances of a similar apocalyptic event in the 21st century are certainly low, maybe just 1 in 500. But the consequences could be just as devastating.